Scientific notation, which is our means of expressing large and small quantities in science. Scientific notation is also called exponential notation because it relies on the use of exponents in the order of 10 to the power of something. We use it to express very large and very small numbers. Powers of 10 will be used with significant figures when we express scientific notation. So in a number that has a limit to the number of significant figures, we will limit the number of reported decimals in our scientific notation based upon that. Scientific notation is a great way of expressing significance in numbers which would otherwise compromise their significance by adding a decimal point in there somewhere. So for instance, if I have several trailing zeros in a number that are not significant, putting a decimal at the end of the number would make them all significant. But if I have at least one zero as a trailing zero that is significant, if I report the number as a scientific notation or exponential notation, I can still report that significant number without reporting the numbers that are insignificant. So we look, for example, at a value, the value 299,792,458 meters per second, which is the speed of light in a vacuum. We can express this to three significant figures as 3 times 10 to the 8 meters per second. When we're considering how this works, consider that the number 10 times 10, which is 100, is represented as 10 to the second, right? 10 times 10 is 10 squared, or 10 to the 2. 10 times 10 times 10, x number of times, would be 10 to the x. If I had 10 to the third, that would be 10 times 10 times 10. 10 to the fourth, 10 times 10 times 10 times 10, and so on. So when we're looking at this number, this 3 times 10 to the 8, we can round 299,792,458 to 300 million. 300 million is the same thing as 3 times 100 million. We know that 100 million is 10 times 10 times 10 times 10 times 10 times 10 times 10. So a total of 10 to the 8. So if we take 3 times 100 million, that's the same thing as saying 3 times 10 to the 8. When we consider algebra, negative exponents in algebra will flip things. So when we look at x to the minus 1, for instance, x to the minus 1 is the same thing as 1 over x to the 1. If we look at what's happening here, x to the minus 1 could be written as x to the minus 1 over 1. We flip the negative exponent to the other side of the fraction, giving us 1 over x to the 1. The same thing is true if it was on bottom initially. If we had 1 over x to the minus 1, we could move it to the top. And then we would have x to the 1 over 1, which gives us the same thing as just x to the 1. For small numbers, numbers less than 1, we report scientific notation using negative exponents. So a number like 0.00001 is the same thing as 1 over 100,000. A number like 0.0000628 is like 6.28 times 1 over 100,000. 100,000 is 10 times 10 times 10 times 10 times 10, or 10 to the 5th. 1 over 100,000 is the same thing as 1 over 10 to the 5th. If I flip that to the other side of the fraction, I can make it negative as 10 to the minus 5th. So I can report 0.0000628 as 6.28 times 10 to the minus 5th for that reason. So we get a final answer of 6.28 times 10 to the minus 5th. If I want to convert between decimal and scientific notation, going from decimal notation to scientific notation, if we are looking at large numbers, those that are greater than 1, they will have positive exponents. We'll move the decimal left until it stops behind the first non-zero digit, keeping track of the significance of my number. So for instance, this number here, 1002030000000, we have a decimal at the very end. In the first number, that decimal does not exist, right? You see no reported decimal in the way that I've written the number the first part. So we're going to assume those last 6 trailing zeros are insignificant. That means our 3 is a level of significance. We'll use the decimal anyway for the purpose of scientific notation. So if we take the decimal and we move it to the first non-zero digit, it winds up after the initial 1. So we have 1.00203000000. The exponent that we use in assigning scientific notation is based on the number of times that we moved the decimal place and will be a positive value. I moved the decimal place in this case a total of 11 times. So that gives me an exponent of 11. I have 1.00203000000 times 10 to the 11th. I will drop digits that are not significant in the original number because we just said that the 3 was the limit of our significance in the original number. We'll drop those 6 trailing zeros and report the final number as 1.00203 times 10 to the 11th. Looking at small numbers, they have negative exponents. We move the decimal to the right until it winds up behind the first non-zero digit. So a number like this, we would move the decimal from the far left all the way behind that first 1. Then the exponent that we will write will be the number of times that we moved it, and it will be negative. So in this case, I moved the decimal 11 places to get behind the first 1. So we have the number here times 10 to the minus 11th. We will drop digits that are not significant in the original number, just like before. All leading zeros are insignificant, so all those leading zeros go away, and leave us with 1.00203 times 10 to the minus 11. Now remember that leading zeros are never significant, they're just placeholders. In converting from scientific notation to decimal notation, looking at large numbers, will have positive exponents. The exponent that's written will reflect the number of times that the decimal moved, and because it's positive, it will be moving to make a number greater than 1. So for instance, if I have this number here, 1.00203 times 10 to the 11th, the 11 indicates that I moved the decimal 11 times. So in order to move back, I will count the number of digits to the right of the decimal, and then add zeros until the number of digits I have total equals the exponent. So for this, I've got 5 digits to the right of the decimal place. Adding 6 zeros brings my total up to 11. So I add 6 zeros in there. If you do add zeros like this, remember that your final decimal will disappear at the end. So when I get that decimal to that last point, I'm going to remove the decimal because by adding those zeros, I've added numbers which clearly are not significant. If they had been significant, they would have been reported in the original scientific notation. So the first thing I'll do then is I'll move the decimal to the right, the number of places indicated by the exponent, and then make sure I keep track of significance in that respect. Then at the end, I will drop the times 10 to the whatever. So for this number, we will move our decimal right 11 times. So we move it right 11 times, and so we have 100.203.0000000 decimal times 10 to the 11th. We will drop the times 10 to the 11th, and then in this instance, because we added those zeros, we drop the decimal. Had there been zeros in the original number, we would still have to drop the decimal here, right? Because we've added extra zeros. That's the problem with reporting things in decimal notation. You can make it difficult to keep track of what zeros are significant. If we're going to convert scientific notation to decimal notation from numbers that are less than 1, small numbers, they have negative exponents. And that exponent, once again, reflects the number of times the decimal moves. So a number like 1.00203 times 10 to the minus 11 moved 11 places, but it moves the opposite direction. We add zeros to the left instead of to the right. And we will add the number of zeros until we have digits equal to the exponent. We will never have more than 1 digit left of the exponent to start, or left of the decimal to start with. So in this instance, the number of 11 means that I have to add 10 zeros. So I add 10 zeros, 10 plus my 1 gives me a total of 11 digits. So I've got this number here. I move my decimal left, the number of places indicated, and then drop the times 10 to the whatever. So here I move my decimal left, and then I can add a 0 in front of the decimal if I want to, doesn't matter. I'll go ahead and do it here. If I add the 0 in front, I'll drop that times 10 to the minus 11 at the end,